is just kind of walk you through, I think, a 10-step process, but it's kind of silly, but it gives you an idea of what is going on in the black box, okay, and what information you have, what information you need, and then how you get to the result. So we start, and these are real data in the Baltimore sample data set. So we have, let's say, 3 houses, 67, 69, and 65. We have a model for the mean. This is our model for large-scale variation, which is a linear trend-surface regression. So this is the price of the house. We regress the price of the house on its x-coordinate and its y-coordinate. Linear. This is just simply this plane I showed you in the previous lecture. You had this plane fit through the little points for Baltimore. That's what it is. This is the plane. Okay? So with this equation in hand, we can get a predicted value for each of these 3 houses. Namely, we plug in x and plug in y, and this is the value we get. So this is a linear, unbiased predictor. It's linear because it's based on a linear regression equation, and it's unbiased because ordinary least squares gives us an unbiased estimate, so therefore the prediction is unbiased. So we could stop here. Now what we know is that because these are observations, we also know what the actual price is. So we can look at how well we did, and we compare the actual price to the predicted price, and we get a residual. And we do this for each of the 3 observed houses. And this is where it starts to be interesting, because now we say these residuals are not uncorrelated. There is some spatial correlation between these residuals. And we can use this information to do better in terms of precision than simply this. Now, we're not interested in doing better for those because we observe them, so we don't need to predict them. We're interested in doing better for a location that we don't observe. That's what it's all about. Okay. So how do we get it? First of all, we need to deal with the mean, deal with the large-scale variation. So we want to predict the price for a house that is at x 909 and y 564. And unlike realistic examples, that's all we need to know about that house. Where is it? We'll give it a price. We'll get the price. And we'll get the price from the trend surface. And then we plug x in here, and we plug y in there, and we compute this. This gives us 57.024 as the predicted value, as the unbiased predicted value. This is what you do when in ordinary least squares you get predicted values and you use them for prediction. Let's say you do a time trend, you fit a least squares line through it, and you plot the next point for the next time period as an extension of the timeline. That's exactly what this is. So this looks at the plane that we have over Baltimore. We pick an x and y, get the point on the plane. That's our predicted price. So this is where standard prediction, non-spatial prediction would stop. We deal with the conditional mean. That's where we stop. Okay? It's not bad because we're unbiased. And it's not, it even has some good variance properties. But it's not the best. Why not? Because we've ignored this spatial structure in the error term. And so now we'll move to exploit that. First, we need the distance between the sample weights. Remember, there's 2 parts to the Kriging weights. One has to do with the covariance between the observations. One has to do with the covariance between observations and the unknown point, the point that we're trying to predict. So we simply take the xy coordinates and compute the distances. That's our distance. Then we need the distances between the sample points and the point that we want to predict. Simple Euclidean distances. We need those. Then we need a variogram. So we need the variogram. We need to do all the squared differences, we need to pick the bins, we need to estimate a value for each of the bins, and then we fit a curve through that. And just to make life simple, I'm taking an exponential semi-variogram which has a nugget parameter and a range parameter, and the nugget is 440 and the range is 28.2. Which means that now for any age, this is 440, this is 28.2, so we just click that in and we get our semi-variance. And then because of the connection between the semi-variance, the gamma h equals C0 minus CH, with C0 in hand, and given gamma h, we can get CH for any h, and that's what we need for any distance. So now we get the CH, this is the result, the theoretical result for the value. We get that plugged in, and we have our 3 by 3 matrix. I mean, this is the same value, I didn't put them all. We have a 3 by 3 matrix. This is our C from the equation. Now we will need C inverse, right? C inverse, and we also need the little c. And the little c is the same thing. We have these distances the 3 distances we computed. We plug in the value of the distances. We have our nugget of 440. We have the range. We plug it in the equation. These are the numbers that we get. So now we have all the pieces. We need to get the weights as the inverse. This is the inverse of the 3 by 3 matrix. And we pre-multiply this with a vector of these weights that we just computed. So the result of this is a vector with 3 values. As you see very quickly, these add up to 1. This is a weighted average of the 3 observations. So this gives us the weights that we need to get our prediction. So the prediction of what? The prediction of the residual, not the price. We already have the large trend, the trend part, the large scale variation part. We're not changing that. We're not touching that. Now we're dealing with the second part, the small scale variation. So we apply the Kriging not to the prices, but to the residuals from the prediction that we used on our observed data points. And now we take those residuals and we plug them in here. We use the weights, and out comes a prediction for the residual at our unobserved location. Because it's unobserved, it's not really a residual in the usual sense of the word, because the residual is the difference between observed and predicted, right? But we don't know what observed is, and we will never know unless we cheat, like we did in the lab. So this is now our optimal, best linear unbiased prediction for the residual at that location. So then to get a better prediction overall, we put the two together. So we have our original trend surface prediction with the prediction for the residual, and this gives us a better, in a mean squared error sense, in a variance, minimum variance sense, a better prediction for the price of that house. Better because we use the second moment. Okay. That's the sense in which it's better. So it's better in the sense that it varies less around the unknown true value. Now both of these are on target on average, but you don't get the average. You don't know what you're getting, right? There's sampling variation, so you don't know which one you're getting. Are you getting one that's close to the true average or one that's far apart? You really don't know that. And to get a sense of this, you could run a simulation, and then you see the full distribution of the errors, whether they're widely spread around the mean or very tight around the mean. And in this case, theoretically, on theoretical grounds, you know that you're doing better in that sense. So then there's two more things. One is we get the variance of the prediction, which again we get by plugging in the nugget and the range into these equations for these covariances. So this is what we get. And then the square root of that is the standard error. And now we're doing predictions. So not point predictions, we want a wedge. And we can say assuming normality, 95% of our predicted house prices will be between 51.6 plus or minus 1.96, that's from the normal distribution, times this standard error. And this gives us a range of the prediction. So then if you want to do some taxation for these houses, you know the range in which you are working, whether you're overtaxing them or undertaxing them. You have some sense of that wedge. So as long as this is a couple of $100, you're not going to worry about it too much. If it gets to be tens of thousands of dollars, then you're in trouble, because then your prediction is not good. That's all it is. Any questions? No, this is a different error.
No?
This is a different error. This is the Kriging. So it gets very confusing, okay? There is a prediction of the mean, right? That is our trans-surface prediction. And then we improve on that by adjusting it. And we're adjusting it by predicting a residual, so to speak. Okay? So then the original value plus or minus that residual gives us our prediction. Okay? That's whatever the number was, 51. Yeah, okay. That's the prediction. Okay? Now that prediction has a variance, the Kriging variance. That's the variance due to the fact that we exploited the spatial correlation. That's the sigma squared, which is the original variance, the variance that you would get from your regression, minus this part that we get from the Kriging part. Okay? So after we compute that, then if you assume normality, then 95% of the distribution is the mean plus or minus 1.96 times the standard error. The standard error of the Kriging prediction, not the standard error that you used to get the Kriging prediction. Right? That is not really a standard error, that's a residual, if you wish. Okay. So it's kind of like cheating, right? You get the mean, and we're so conditioned to think about this that we're done, right? You estimate your regression, and then you say, well, what if income was twice as large? Well, you plug in the new value for income with the same coefficient, and boom, you have a point estimate. You stop. Okay? This is fine when your error terms are classic error terms and uncorrelated constant variance. But even when they're heteroscedastic, it's not fine. Then you should take that into account. And there's some, I think it's a classic paper by Goldberger in Econometrics. It's ancient, in the 60s or even in the 50s, on best linear and biased prediction. That's Kriging, but viewed from the economist, econometrician perspective, as a way to improve the properties of a predicted value by taking into account the fact that the covariance, the error variance covariance matrix, is not sigma squared I, but is a full matrix. And I can dig up the reference, but it's a classic reference on that. And if you've taken econometrics, I don't know if you have, but it's one thing to estimate, it's another thing to do predicted values. How do you get the standard errors of your predicted values? And this method goes a little further than just the point estimate and improves on that point estimate. So what does that mean, improves on? It means it changes it. Okay, so we started off with, I forgot, 57. We don't stick with that, we change it. In fact, we make it smaller. And how much smaller? Well, that comes out of the Kriging. And so the Kriging tells us how we should adjust this prediction that we get from the large scale model from the trend surface. And because we don't actually observe these locations, we don't really know how well we do. But we know because of the math that this is optimal in in practice, as you will see, and as you've already seen, it's not as simple as it sounds. I mean, just to tell you, Luis and I were working on this to try to get the lab that he did in geostatistical analyst to match with the lab that I did in GStat to get the same values for our predicted values, and it was, you know, it took some work. We got close. Close enough, but it wasn't exactly the same. Because there's all kinds of things going on in the black box, you know. How many intervals, how wide are the intervals, how many points do I use? Do I use all the points or only the semi-variogram? Do I, in the moving window, you know, instead of inverting all the points, how many points do I take in the moving window? Is it the same for all the points? Does it vary with the points? Do I take all the points? So these kinds of things are all variables that get you a different prediction. And so it's very important that you do cross-validation or some other way of checking how well you're doing with those predictions, because, you know, just doing click, 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 you know, it looks great, but you really can't tell how good it is unless you've tried some other models and changed some of the assumptions behind the model. And one thing that is kind of, well, I wouldn't say misleading, but it's kind of dangerous in that a geostat analyst uses all the points, whereas most of the textbook treatments and the classic software, which is all based on GSLib, you may have seen this. This is a library developed at Stanford, and a lot of the stuff in GStat is actually drawn from that. It's a public domain Fortran library. You can download it. And all that stuff is in there. That uses the semi-variogram. So it uses 10 points, 12 points, you know, 15 points. That's it. Whereas geostatistical analyst uses all of them. And so you can, I mean, it's hard to say for me, I can't judge which is better because I don't know and I can't tell. And from looking at the manuals, we couldn't figure out what estimation method geostat analyst uses to get the curve fit. Is it least squares? Is it nonlinear least squares? Is it weighted nonlinear least squares? You know, is it some kind of hybrid? I remember not finding this in the manual before, and we couldn't find it. So that's a black box part. I mean, it's very powerful and it's very easy, and if you're in a hurry, I would definitely recommend it. But, and I've used it. You know, usually I am in a hurry, so it's great for that. But there's lots of question marks. And if you're really interested in geostatistical analysis, I would really recommend that you dig a little deeper in GStat and some of the other software where I mean, they don't make it easy on you. The ArcGIS makes it easy for you. All you have to do is pick a couple of options and boom, there's your map, you know. In GStat, you really have to think about it, you know. What is the interval? How many points? Which model? You know, which estimator to get the parameters? And that's a good thing because there are trade-offs involved in each of these. And before you use these incredibly powerful techniques, you should really have a good sense of the trade-offs involved, or you can do nonsensical, great-looking nonsensical stuff. So the second assignment will be just a straightforward, I'll try to get it ready tomorrow, maybe. A straightforward application. Here's a sample. Get the variogram, fit the curve, get the Kriging prediction, and do leaving one out type of prediction so you get a sense of how well you did. So you use one, say a spherical model and an exponential model, or a spherical model with one set of parameters and one with a different set of parameters, and then compare them in terms of how well they do for this one point that you left out of the sample, because then you can tell. And that's enough to get a sense of what's involved in this thing.